Hi all, my name is Rajeev. I'm a student at Johns Hopkins. This is a joint work with my colleague Vishwa and my advisor Vishal Patel. This work is on transfer learning for image deraining, where we leverage unlabeled real-world data to improve generalization. Existing approaches for image deraining follow a fully supervised paradigm and hence they require a paired training data. However, it is difficult to collect paired training data for the task of image deraining, due to which existing methods train on synthetic data. This results in a domain gap when these networks are employed on real-world data, resulting in suboptimal performance. Hence, it is necessary to leverage real-world data in the training process. With this motivation of leveraging unlabeled real-world data into training process, we follow a semi-supervised learning paradigm. Here, we consider synthetic data as labeled data and real-world data as unlabeled data. Based on this, we propose a multi-stage Gaussian process-based pseudo-labeling approach. More specifically, the proposed approach contains two training phases, labeled and unlabeled phase. In the labeled phase, we train on synthetic data by minimizing the reconstruction error between the predictions and ground truth. In addition, we save the latent space vectors of the labeled data, which we use in a later stage for the pseudo ground truth computation. In the unlabeled phase, we compute the pseudo ground truth by modeling the joint distribution of latent space vectors of labeled and unlabeled data using Gaussian process. Then we use this pseudo ground truth to supervise the network in the latent space. We iterate over these two stages. The key idea behind the pseudo ground truth computation is that we can express the latent space projections of the unlabeled data as linear combinations of the predictions of the labeled data. With this formulation, we can model the joint distribution of the labeled and unlabeled latent space vectors using Gaussian processes. Conditioning this joint distribution on labeled latent vectors will yield the following multivariate Gaussian for the unlabeled vectors. The mean and the covariance have the following closed form solutions. In our approach, we use this mean as the pseudo ground truth as supervision for the unlabeled data. The overall loss function for the unlabeled data is given by the equation, which consists of two parts. The first part minimizes the error between the prediction and the pseudo ground truth, and the second part minimizes the variance. The figure summarizes the overall approach, which consists of two phases, labeled and unlabeled phases. In the labeled phase, we minimize the reconstruction error on the labeled data. In the unlabeled phase, we minimize the error between the prediction and the pseudo ground truth in the latent space. We evaluated our method on DDN-SIRR dataset, which consists of labeled synthetic and unlabeled real-world data. The state-of-the-art method with synthetic-only training, which is from CVPR19, achieves a PSNR of approximately 20 dB. Another method, based on Gaussian mixture models for transfer learning, achieves a 1.6 dB improvement over the baseline by leveraging the unlabeled real-world data. In contrast, our method is able to exploit the real-world data better and achieves an improvement of 2.1 dB over the baseline. In addition, we conducted semi-supervised learning experiments on Rain100 dataset to demonstrate the effectiveness of the proposed approach. Specifically, we vary the percentage of labeled data used for training from 10% to 100%. With 100% of the data used for training, the network achieves 23.7 dB. With our approach, we are able to achieve comparable performance with limited labeled data. Further, the proposed method is able to achieve the fully supervised performance with just 60% labeled data. Thank you for attending our talk on transfer learning for image deraining. The code is available in the following link. Please visit our poster session for more details.